dx over x plus 1 times x squared plus 1. Okay, so the first thing you have to do is the partial fraction part, right? So if we think about taking our fraction 1 over x plus 1 times x squared plus 1, so it has two pieces. It has this piece here, which is a linear factor, and it has this piece here, which is a quadratic factor. So the linear factor is going to get an a over x plus 1, and the quadratic factor is going to get a bx plus c over x squared plus 1. Does that make sense? Yeah, so exactly what you wrote. And so now I'm going to clear the denominators by multiplying by x plus 1 times x squared plus 1. So on the left-hand side, we get 1, and then we get a times x squared plus 1 plus bx plus c times x plus 1. And then we can pick some values of x to help us out here. So what's one of the values of x that I could pick that would help us out? Okay, right, -1. So if x is equal to -1, we get 1 is equal to a times -1 squared plus 1 plus b times -1 plus c times -1 plus 1, right? So this whole part goes to 0. We end up with 1 is equal to 2a, so a ends up being equal to 1/2. Okay, so then what can you do? Yeah, so we want to plug in, so we could plug in the 1/2 for a. Yeah, I was actually going to say, if you pick x equals 0, I probably would pick x equals 0. So if I do 0, I have 1 equals a times 0 squared plus 1 plus b times 0 plus c times 0 plus 1. So the b times 0 part goes to 0. So we end up with 1 is equal to a plus c. And then we know a is 1/2, right? So 1 is equal to 1/2 plus c. Excuse me. So c is going to be equal to 1/2 as well. And then we can do the same thing. We can pick another value for x so that we can find b, because we'll be able to plug in a and now c. So what's another value you could pick? Yeah, so 1. I figured that's what you meant. So 1 is going to be equal to a times 1 squared plus 1 plus b times 1 plus c times 1 plus 1. So 1 is going to be equal to 2a plus b plus c times 2. So 1 is going to be equal to 2a plus 2b plus 2c. And a we know is 1/2, and c we know is 1/2. So 1 is going to be equal to 2 times 1/2 plus 2b plus 2 times 1/2. So 1 is going to be equal to, this part here is going to be 1. This is going to be 1. So 1 plus 1 is 2. So 2 plus 2b. So b is going to be equal to -1. Oops, 2b is going to be equal to -1. So b is going to be equal to minus 1/2. That's terrible looking too, but. So our fractions end up being, right, you have a, which is 1/2. So we end up with 1/2 over x plus 1 plus 1/2 x, minus 1/2 x plus 1/2 over x squared plus 1. Right, if I plug that in. It's okay. It's easy to drop constants. Does anybody have any questions with what I've done so far? Yeah. Yeah, so that's right. So that would, if you don't get the right B, it's going to mess up the rest of the problem. But just to finish the problem, right, to kind of see it again. So let me select this so that we can take it to the next page here. Okay. So record, paste. Okay. So now we are ended up with the integral of this first part, right? So I could really write this as 1/2 1 over x plus 1 dx plus the integral of minus 1/2 x plus 1/2 all over x squared plus 1 dx. And I could split up that second integral. So I've really got 1/2 the integral of 1 over x plus 1 dx minus 1/2 the integral of x over x squared plus 1 dx plus 1/2 the integral of 1 over x squared plus 1 dx. So any questions on how I got any of those? No. Okay. So now the first one I can just integrate. This one here is going to end up being 1/2 the natural log absolute value of x plus 1. That's that trick I talked about. This second one I can use u substitution. So u is going to be x squared plus 1. So du is going to be 2x dx. So I need a 2 in here, but to balance it, I need another 1/2 out here. So we end up with minus 1/4 the integral of 1 over u du, or minus 1/4 natural log absolute value of u. So this is going to be minus 1/4 ln absolute value of x squared plus 1. And then the last one is just the derivative of inverse tangent. So this is going to be plus 1/2 tangent inverse of x plus c. Questions on any of that? Oh, yeah, you're right. There were bounds. Whoops. Get rid of the plus c. The bounds were what here? 0 to 1. Okay. So we're going from 0 to 1. All right. So we're going to have 1/2. When I plug in 1, right, we're going to have 1/2 the natural log of 2. You can put in absolute value, or you don't have to because 2 is positive. Minus 1/4 the natural log of 2. Plus 1/2 the inverse tangent of 1 minus 1/2 the natural log of 1 minus 1/4 the natural log of 1 plus 1/2 the inverse tangent of 0. So the natural log of 1 is 0, right? So each of those pieces. How did I get inverse tangent? So 1 over x squared plus 1, that's just the very basic, the derivative of inverse tangent is 1 over x squared plus 1. So if you're integrating 1 over x squared plus 1, it's just going to be inverse tangent. So let's see. So we've got here 1/2 natural log of 2 minus 1/4 natural log of 2 plus, okay, when is the tangent equal to 1? So we're trying to figure out what the inverse tangent of 1 is. So it's going to be 1/2 times something. So what value is the tangent equal to 1? Yeah, pi over 4. Because remember, the inverse tangent is defined in quadrants 1 and quadrants 4. So 1/2 times pi over 4. minus, we have a bunch of zeros, right? So minus 0, minus 0, plus 1/2, and what's the inverse tangent of 0? So when is the tangent equal to 0? At 0. So that whole second piece is just 0. You could put those first two pieces together, right? I have 1/2 of like this value, natural log of 2, minus 1/4 of this value. So it's technically just 1/4 natural log 2. If you leave it as 1/2 ln 2 minus 1/4 ln 2, that's fine too. Plus pi over 8. Does that help? Thank you for reminding me about the bounds. No problem. Any other questions?
Dr. Carmen, Can you just really quickly explain the bounds, please?
Like how I, like where I got them from, or how I...
I noticed that you adjusted them. So how did you do that?
I didn't adjust them. They're the original bounds. So the original problem went from 0 to 1.
Oh, okay.
So I just waited until I was at the very end of the problem, and then I just used 0 and 1 again. So I went all the way back to x's. In the solutions, I might have changed them, but in this one, I didn't. Does that answer your question?
Yes, thank you.
No problem. I know it's hard too because stuff, I don't have a big chalkboard in a classroom where we have the whole entire problem at once where you can see it. Other questions? In the final answer, no, it's a positive 1/4 because you have 1/2 minus 1/4. So remember 1/2 is 2/4. So 2/4 minus 1/4 would give you a positive 1/4. Other questions? No. Okay. Then last class we were talking about L'Hopital's rule. So that's what we're going to keep talking about here today. So that was section 4.10. So this is, 4.10 continued. And so last class we talked about how we had there's other indeterminate forms besides 0 over 0, infinity over infinity, right? If you have 0 over 0 or infinity over infinity, you can just straight off the bat use L'Hopital's rule. But if you got one of the other indeterminate forms, right? So we talked about indeterminate forms, so kind of quick refresher. So 0 over 0, infinity over infinity. And then we also said you had infinity times 0, infinity minus infinity, and 1 to the infinity, 0 to the 0, and infinity to the 0. And so these first two here, these you can just apply L'Hopital's rule. I said these next two here, which is what we had done an example of, you have to use algebra to get into 0 over 0 or infinity over infinity. And then, go back to green here. These last three, wow, that is really laggy. These last three, you have to, yeah, there is. This happens sometimes with Zoom, or with, it might be my internet connection. Let me let me stop the video. All right. So if you're watching the recording, be sure to look at the last page in the PDF because I forgot to hit record. I'm so sorry. Okay. So we are going to do one more problem here. And so this one is the limit as x approaches 0 from the plus side again of sine x to the x power. So if I try to plug in, right, I end up with the sine of 0 to the 0 power. And the sine of 0 is 0, so I end up with 0 to the 0 power. So rather than look at this limit, we're going to come back to this limit. But what we're going to do is we're going to kind of take a pause and we're going to look at a related limit. And that related limit is going to be, rather than look at the limit of this function, we're going to look at the limit of the natural log of this function. So we're going to look at the limit as x approaches 0 from the plus side of the natural log of the sine of x to the x. And the reason that we're going to look at this is because what taking the natural log does is it allows us to bring the power that's stuck up there down in front, right? So remember, if you have the natural log of x to a power, you can pull the power down in front of the natural log. So our issue right now is that we have a base and an exponent that kind of together don't make a lot of sense. So we want to kind of break it up, and the way to break it up is to get the exponent down. So if I look at this limit, but if I tried to plug in right this second, I'm still just going to have a mess. So the first thing I'm going to do is I'm going to pull that x down in front. So we have x ln sine x. And so now if I try to plug in, we end up with 0 times the natural log of the sine of 0. Remember, the sine of 0 is 0, so we have 0 times the natural log of 0. And if you remember your log graph, it looks like this. So as I come into 0, and we are coming from the positive side, so as I come in from the positive side, the natural log approaches negative infinity. So really what I have is 0 times minus infinity, which is one of those indeterminate forms, right? I wrote it earlier as 0 times infinity. If you have 0 times negative infinity, it's the same indeterminate form. So questions on what I've done so far. I still haven't solved anything. And I've taken a pause from my original problem, right? So I've kind of created a brand new problem by taking the natural log. No. Okay. So I'm going to do some algebra to rearrange this. I need to get this to be 0 over 0 or infinity over infinity. And there's not like a great way to look at this. But if you happen to have two things multiplied together, you can rewrite them as a fraction. So this is actually the same as the natural log of the sine x divided by 1 over x. So if you think about it, if I were to do out that division, keep the top, change the multiplication, flip the bottom fraction. When I flip 1 over x, it becomes x over 1, and I would get back to what I started with. So this is kind of a common trick that we use. If we're trying to kind of force something to be a fraction, you can always take two things that are multiplied together and force it to be a fraction by taking one of those things and dividing by 1 over whatever it is. So that's all I did there. Questions? Okay, so now if I try to plug in, we still have the natural log of the sine of 0, which we know turns out to be minus infinity. On the bottom, I have 1 over 0. Well, we talked about how 1 over 0 goes to infinity as well. So I have minus infinity over positive infinity. It doesn't matter if you have a minus, if you have two minuses, you have one minus, you have no minuses. You have infinity over infinity. And so now we're in a place where we can do L'Hopital's rule. So limit x approaches 0 from the plus side. Okay, so we're looking at how do we take the derivative of the natural log of the sine x. Okay, so it's 1 over sine x, so 1 over the stuff times the derivative of the stuff, and the derivative of sine x is cosine x, so it's 1 over sine x times cosine x, and then if you think about 1 over x, right, 1 over x, remember, this is the same as x to the negative 1, so how do I take the derivative of that?
X to the negative 2 times negative 2.
So it's x to the negative 2, but it's not times negative 2. So it's not natural log of x, because if you integrated 1 over x, you get natural log of x. So we're close. David was close to what it was. So remember, like, what's the derivative of x cubed?
3x squared?
Yeah, so the derivative of x cubed is 3x squared. You took the power came down in front, x to the power minus 1. It's the same deal here. So we're going to take the power minus 1 to x to the power minus 1. So it's minus x to the minus 2. So you're not integrating it, right? So that's the important thing to kind of realize. When you integrate, that's when you change the power and then divide by the new power. Okay, so if we tried to plug in right this second, we're still going to have a giant mess on our hands. So we actually at this point want to do some algebra to kind of clean up what we have. So remember the top part here, what we really have on the top, we have the limit x approaches 0 from the right of cosine x over sine x. And then my bottom is now minus 1 over x squared. So I have a fraction over a fraction. And now I can do keep, change, flip. So we've got the limit as x approaches 0 from the right side of cosine x over sine x times minus x squared over 1. Or I right now have the limit as x approaches 0 from the right side of minus x squared cosine x all over sine x. So you could change cosine over sine to cotangent, but then you still have a problem because the cotangent of 0 is undefined. So while, yes, you could change it to another trig function, it's not actually going to help you out here. So if I plug in now, I get minus 0 squared times the cosine of 0 divided by the sine of 0. And so this actually still just turns out to be 0 over 0. Which you might be going, gee, are we ever going to finish? Yes, we are going to finish. But in this case, we have to go one more time. It happens a lot in L'Hopital rule problems. Sometimes you have to go 2 or 3 times. So we're going to do L'Hopital's rule one more time here. Hopefully this is the last time. So the limit as x approaches 0 from the plus side of, okay, so the derivative of the top, we have to use the product rule. So first, minus x squared times derivative of the second, so times minus sine x, plus the second, cosine x, times derivative of the first, minus 2x, all over, now the derivative, we just look at the derivative of the bottom. Derivative of the bottom is cosine x, right? So, again, remember L'Hopital's rule, we're not doing the quotient rule, right? We're not doing bottom derivative of top minus top derivative of bottom all over bottom squared. We're literally taking the derivative of the top part, and then we're taking the derivative of the bottom part. And now I'm at a point where I can plug in. So we're going to get minus 0 squared minus sine of 0 plus the cosine of 0 times minus 2 times 0 divided by the cosine of 0. So both of those pieces on the top are 0. So 0 plus 0 divided by the cosine of 0 is 1. So we end up with 0 divided by 1, which in fact is just 0. So 0 divided by 1 is not another time when you would use L'Hopital's rule. It just actually turns out to be 0. Questions on what I did so far? We're still not done with the problem. I know it looks like we're kind of done, but we're not done yet. But before I go on to the final last step, so that then we can actually be done, does anybody have any questions so far?
Dr. Gorman?
Mm-hmm.
What's that part that says cosine 0 is
let me, this part here, right?
Yes.
Yeah, I'm just plugging in, so it's minus 2 times 0. I kind of squished it in there. Sorry about that.
Okay. Thank you.
No problem. Yeah, so the ln of 0 equals negative infinity is all based off of this graph up here, right? So up here, this is the graph of the natural log of x. So as I'm approaching x equals 0 on the natural log of x, I'm going down towards negative infinity. Does that help? No problem. Any other questions? No? Okay, so at the very beginning, right, I had a problem and I couldn't solve that beginning problem. And then I took the natural log. So I looked at a related limit. I took the natural log of what we were looking at. And I was able to get an answer. But this answer tells me the limit of the natural log of the function. So basically now I'm looking for, what we're really looking for is the limit of the original function. So the limit as x approaches 0 from the right of sine x to the x. So when you take a natural log, what is the inverse thing? So like a square and a square root undo each other. So what undoes a natural log? Yeah, e. So taking e to the x undoes the natural log. So what that means is I have to take e to my answer to get the original limit. So since my answer here was a 0, I have to take e to the 0 power here. And so that is actually going to be equal to 1. If here I had a 2, my answer here to the original problem would have been e squared. So you have to to undo the fact that we took the natural log, you have to take that and raise e to whatever power you end up getting. Questions? Yep, so the final answer is 1. Yeah. Yeah, that's a, yeah, so, okay, let me see, is the video laggy for everybody? Okay, okay, so, Ariello, you might want to, like, disconnect and come back if it's super laggy. That usually will fix it. Okay, so what I did for the last thing was this part here, all of this work that I did here, that was to find this limit, and this limit has this natural log in it, right? And so I want to undo the natural log. So the way to undo a natural log is to take e to whatever power, right? So if I have e to the ln of x, I just end up back with x. And that's because e and natural log are inverse functions of each other. So since my original problem is just the integral of sine x to the x, this part here, and I now found that the answer to the limit that has the natural log in it ends up being 0, I need to undo the natural log, right? I added that natural log in at the beginning of this problem. And so now I need to undo it. So to undo the natural log, I have to do e to whatever the answer I get from this problem was. So that undoes the fact that I took a natural log at the beginning. So that's how I'm doing e to the 0. And that, in this case, that ends up being 1. So whatever answer you get from the natural log problem, you have to do e to that power to undo that. Does that help? For every problem, so be careful, for every problem that you add a natural log in. My original problem, if my original problem had a natural log, like, that doesn't mean I need to do the e. But I added this natural log in. So since I added this natural log in, then I have to undo it at the end. Well, so the 0 is the limit of the natural log of sine x to the x. Yep. So this 0 down here is the answer to this limit problem, not the original problem we were given. Right, and then we raise it to the e to get the answer to the original problem. Other questions? You don't come across these problems like a whole ton, but you come across them like sometimes. So that's kind of why we wanted to do this, and like to be able to I don't know that you really wrote it wrong exactly, Robert, but so I want to show you one example in case you run into one of those indeterminate forms where you have the exponent is different, or you have an indeterminate form that has that exponent. Other questions? No? Okay. So let me stop to keep recording. So what we're going to do now is actually section 9.7. So it's the last section before the test. And this is about improper integrals. Okay, so when you're taking an integral, there are two things that could kind of go wrong. So two things that could go wrong with an integral. And when we say, I should really say with, I should be a little more careful, with a definite integral. So, if you remember back to Calc 1, a definite integral talks about the area under a curve, right? So, one of the things that could go wrong is that one of our limits of integration could end up being plus or minus infinity, right? So then it's kind of like you're talking about the area, an infinite number of area. So you're not really sure exactly what's going on. So the first thing is that the limits, I should say, the limits of integration could involve a plus or minus infinity. So that's going to be an issue. The second thing is that we could be, the interval, the limits of integration creates, is a place where, I should say contains a place, contains a place where the function is undefined. So those are the two things that could go wrong, right? So if you're thinking about area under the curve, right? So like if you think about, say, for example, y equals 1 over x, right? Remember, 1 over x looks like this. And let's say you tried to integrate 1 over x from -1 to 1. Well, you're talking about the area under the curve, and now you have a problem because this area just goes on forever. And this area here goes on forever, and so you don't really know what happens, right? Because there's nothing that kind of stops the function. So that's what I mean by there creates an interval where the function is undefined. And so you can, sometimes people do this in Calc 1, they'll put on a test, find the integral from -1 to 1 of 1 over x. And, everyone's like, integral 1 over x, natural log x, evaluated from -1 to 1. And you get an answer, but that's not necessarily the right answer because you have integrated over this part where stuff was undefined. So going back to how we defined an integral and all that stuff, you need the function to be continuous and you need it to be defined everywhere where you're integrating. So we're going to talk about today, what happens if that's not the case? What if I do have a place where the limits are plus or minus infinity, or I have a place where the function is undefined? What do I do? And so the answer is you replace the bad limit of integration within limit. So what do? We're going to replace the bad limit of integration with an actual limit. And when we integrate, when we do this, after we replace this bad limit, we're going to integrate like we normally do. Then we're going to evaluate the limit. And if we evaluate the limit, so if we get a number answer, if we get an actual number answer, then we say the interval converges to that number. What is the word after creates? Contains. So if we get an actual number answer, then we say the interval converges to that number. If we don't get a number, if we get infinity or negative, plus or minus infinity as our answer, if plus or minus infinity is our answer, then we say the interval, or the integral, not interval. Oh, I wrote interval up here too. That should be integral. The integral number answer converges to that number. If plus or minus infinity is our answer, then we say the integral diverges. So basically, the word diverges is saying that your integral blows up. Either it blows up positively or it blows up negatively. And so that's all a lot of words. So I'll give you a moment to copy it down. We are going to, I'm going to make sense of this. We're going to do examples, and I think it'll make a little bit more sense.
Professor, what does it say after plus or minus infinity is a?
So if plus or minus infinity is our answer, I know I got sloppy. I'm sorry.
Is our?
Yeah, this says.
Thank you.
No problem. This says is our answer. Then we say the integral diverges. Okay, so can I go on to the next page? Yeah. Okay. Okay, so let's do some examples. So determine if the integral, or if the integrals converge or diverge. So, A. The integral from 1 to infinity of dx over x. Okay, so the first couple examples we're going to do are going to be the ones where we have limits that are plus or minus infinity to kind of get us used to working with this stuff. So I have that upper limit is infinity, and that's a problem. So what we're going to do is we're going to replace infinity with some letter. Now, usually we're used to, when you first learn integrals, you have the integral from a to b of f of x dx. So if we're replacing an upper limit, we usually use a b, and if we're replacing a lower limit, we usually use an a. And so this integral here with this improper this improper integral with this infinity up there, this is actually going to be the same as saying the limit as b approaches infinity of the integral from 1 to b of dx over x. So all I've done is taken that upper infinity limit, which I know is an issue. I replaced it by a letter, b, and then I still want to think of it as infinity, so I'm thinking of it as the limit as b approaches infinity. Questions? Okay, so then now what I'm going to do is I'm actually going to do that integral. So what's the integral of dx over x? Yeah, natural log of the absolute value of x. So we still have this limit. So the limit as b approaches infinity, the natural log, absolute value of x, evaluated from 1 to b. And then, just like before, we're going to plug in the top limit, plug in the bottom limit. So we've got the limit as b approaches infinity, natural log, absolute value of b, minus natural log of 1. Remember, the natural log of 1 is 0, right? So this part goes to 0. So this is just going to be the limit as b approaches infinity of the natural log of the absolute value of b. Okay, so if I plug in the natural log, if I plug in infinity for b, right, we end up with the natural log of infinity. And we usually don't write that, right? So it's kind of like, I'm going to put those quotes around it because it's kind of like bad mathematics, a little slangy. But this is where knowing the graph of the natural log is really helpful, right? So remember, the natural log starts out and pretty slow, right? And then it grows, and it keeps growing forever, but it grows pretty slowly. So what happens to that graph as x goes towards infinity? So what's happening as I'm going towards the natural log of infinity? Yeah, so this whole thing ends up being equal to infinity, because the natural log of infinity is just infinity. And so then my final answer here, I got infinity, and what that means is that this diverges. I didn't get a concrete answer. I didn't get like 5 or 17 or 1.7 or pi or e. I didn't get any of those. I got infinity, which means that my answer is going to diverge. Questions? Getting close to being ready for NASA. Okay, so let's try another one. So b, the integral from 1 to infinity of 1 minus x e to the minus x dx. So again, that issue is that infinity. So I'm going to replace it with the limit as b approaches infinity of the integral from 1 to b of 1 minus x e to the minus x dx. Okay, so we have to figure out that integral. I'm going to kind of do the integral separately. The reason I'm going to do the integral separately is because I hate having to keep writing limit as b approaches infinity on all these lines that have to just do with the integral. So often, if it's a more complicated integral like this one, I'm going to come over and do it as a separate integral. So we're looking at the integral from, and I'm not even going to worry about the exponent, the 1 to b yet. I just want to figure out what that integral is. So if we look at the integral of 1 minus x e to the minus x dx, what do I need to use to integrate that?
U sub?
Okay, so U sub isn't a bad idea, but what would you try making your U?
1 minus x.
Okay, so yeah, so let's look at this. Don't write it down yet, but if you let u be 1 minus x, then du is just going to be dx, and I still have the e to the minus x part. So that's kind of still giving me an issue. So u sub wasn't a bad idea to try, but it's actually not going to work out in this problem. A couple of people said integration by parts. So yeah, so right, I have two things that are multiplied together. They're not exactly related to each other. So this is a good candidate for integration by parts. So integration by parts, remember we need the u and we need the dv. So what would we make the u? Okay, so yeah, so remember that laete, right? So we don't have any logarithms, we don't have any inverses. The next thing is algebra. So 1 minus x is an algebraic function. So you want to use the 1 minus x as the u, and then the dv is going to be e to the minus x dx. So du is going to be just minus dx, right? Because the derivative of 1 is 0. The derivative of minus x is negative, so minus dx. To find v, we're going to integrate this. So the integral of e to the minus x dx, which is going to be minus e to the minus x. Right, we've done that a bunch now. And so this is going to become uv, right? So 1 minus x times minus e to the minus x minus the integral of v du. So minus e to the minus x times minus dx. So if I make this a little nicer, I really have minus 1 minus x e to the minus x minus the integral. So inside the two negatives cancel each other out, and we have e to the minus x dx. So we've got minus 1 minus x e to the minus x. And then the integrating e to the minus x gives me minus e to the minus x, so minus times minus is plus. So plus e to the minus x. Questions on my integration there? No. Okay. So this is now going to be equal to, I can come back up here to my original problem. We have the limit as b approaches infinity of the stuff I just found. So minus 1 minus x e to the minus x plus e to the minus x evaluated from 1 to b. So if I plug in b, I get minus 1 minus b e to the minus b plus e to the minus b minus 1 minus 1 e to the negative 1 plus e to the negative 1. Oops, and I forgot my limit. Right, don't want to drop your limit. Equals the limit as b approaches infinity. So that second piece is fairly nice, right? 1 minus 1 is 0, so that first piece drops out. So this is going to be equal to the limit as b approaches infinity of minus 1 minus b, e to the minus b, plus e to the minus b, plus e to the negative 1. And remember, e to the minus b, that's just 1 over e to the b, right? So I can make this a little nicer looking to help us figure out the limit as minus 1 minus b over e to the b plus 1 over e to the b plus 1 over e. Questions on anything I've done so far? No. Okay, so remember, if I'm taking the limit of a bunch of different pieces, I can take the limit of each piece. So this is going to be the limit as b approaches infinity of negative 1 minus b over e to the b plus the limit as b approaches infinity of 1 over e to the b plus the limit as b approaches infinity of 1 over e. And so I broke it up because the second and the third limits, they're actually pretty easy and we can just get the answer. But the first limit is going to take us a little bit of work. So let's start with the last limit. That's actually the easiest one here. So 1 over e. Oh, and I should be a little careful, right? This negative here should have distributed to this e, so these here should be negatives. So I'm going to fix that here. So this is e to b. This should be minus the limit, because that should be minus. Sorry about that. And this here is a minus, so minus e to the negative 1. Okay, so that last limit, there's no b's in that last limit, right? So here, there are no b's. Since there are no b's, there's nothing for me to plug b into, so the limit is just 1 over e. So this last one here is just minus 1 over e. The middle limit, if I plug in, I would have 1 over e to the infinity. E to the infinity is just infinity. So it's 1 over infinity, and 1 over infinity is just 0. If I plug into the first limit, we end up with negative 1 minus infinity over e to the infinity. And so this is just infinity over infinity, right? I have some ginormous number on the top and a ginormous number on the bottom. So for that first piece only, I have to do L'Hopital's rule again. So we're going to end up with the limit as b approaches infinity. The derivative of the top, so I have minus, and then the derivative of b is, I have a minus b. So the derivative of minus b is negative 1. Divided by derivative of e to the b is just e to the b. So this would just be 1 over e to the infinity, which also is going to end up being 0, right? Because e to the infinity is infinity, and 1 divided by something super, super huge is really, really tiny. So it's going towards 0. So my whole entire limit is 0 plus 0 minus 1 over e. So my whole entire limit is minus 1 over e, which means, let me pick this up here a little bit, which means that it converges. So it converges to minus 1 over e. Questions? Yeah, so the diverges and converges depends on what your final answer is. So what minus 1 over e is a number, right? So it's an actual like physical number. If you get an actual physical number, then it converges. If your answer ends up being, your total answer at the end ends up being positive infinity or negative infinity, then it diverges. Does that help? No problem. Any other questions? So sometimes you still have to use all the techniques that we've been using before, right? That's kind of what made this problem ugly. It wasn't so much the limit part. It was the fact that we still had to use integration by parts, which still gave us kind of a messy function to kind of work through. Yeah, so if your answer, right, when you get down to the end, if your answer is, so I'll kind of write it here. So if your answer, when you're at the end, if your answer is positive infinity or negative infinity, these two mean it diverges, right? So if you looked at that last example that we did, at the end I got infinity, so my answer diverges. If you get some actual number, so like, I know negative 1 over e, it's not like 7, but it is like 7. Remember, e is a number. It's a decimal that never ends, but it is an actual physical, like, number. So if you get a number, then it converges. Does that help? No problem. Any other questions? No? Okay. So let's try another one. The integral from minus infinity to infinity of e to the minus x dx. So this one has both a positive infinity and a minus infinity, right? So both of those cause issues. So we actually need two separate limits. We need one limit that's taking care of the negative infinity part, and we need one limit that's taking care of the positive infinity part. You could write the limit of something, but that's kind of messy, and so we actually end up using a trick from Calc 1. So I just want to pick a nice number. So like, what's the nicest number that's between minus infinity and infinity? Okay, 1 works. So yeah, 1 works, 0 works. I think 0 is a little nicer than 1, but if you picked 1, you could do what I'm going to do here with 0, the exact same thing with 1. So if you remember in Calc 1, you can actually split an integral. So I can make this integral go from minus infinity to 0 of e to the minus x dx. plus the integral from 0 to infinity of e to the minus x dx. So remember, as long as the upper limit here on this first part matches the lower limit on this second part, then I can put the two integrals together. So basically I've split this now into two separate problems. Questions about me splitting it? No? Okay, so for each of these I'm going to have to make a limit. So this is going to end up being the limit as a approaches minus infinity of the integral from a to 0 of e to the minus x dx, plus the limit as b approaches positive infinity of the integral from 0 to b of e to the minus x dx. So I've gotten rid of the bad part. I essentially have two problems to do now, right? I have the one limit, the first one, and then I have the second one. They are two completely separated limits, right? So I can just work the first limit, and then I'll work the second limit, and then we'll talk about what the answer should be, because we need to put the things from the two limits together. So if we just work strictly on the left limit, the integral of e to the minus x is minus e to the minus x. So this is going to be the limit as a approaches minus infinity of minus e to the minus x, evaluated from a to 0. So we're going to plug in the top number. So we're going to plug in 0 on the top. So we end up with the limit as a approaches minus infinity of minus e to the minus 0 minus, we're going to plug in a from the bottom limit, so minus e to the minus a. So e to the minus 0, that's just e to the 0. So this whole piece here is just going to 1. So this is going to be equal to the limit as a approaches minus infinity of 1 plus e to the minus a. And so if I plug in infinity, I end up with 1 plus e to the minus infinity, or 1 plus e to the infinity, which is 1 plus infinity, which is infinity. Questions about what I did? No. Okay, so here's the deal. As soon as one of your pieces diverges, the whole entire thing diverges. So since my first piece here ended up going towards infinity, I can say that the whole entire limit diverges. If this first piece had given me like 3, then I would need to figure out that second limit and add the two pieces together. So like if the first piece was 3 and the second piece was 7, then your limit would actually be 10, and so that would be the value of your integral, would converge to 10. But as soon as one piece diverges, save yourself the trouble. You don't have to worry about doing the other piece. The whole entire thing is going to diverge. So it's not like bad on one side can balance out bad on another side. Can't do it. As soon as one side is bad, the whole thing is bad. Questions? No? It's not terrible, right? Like, they're not great, but it's not terrible. You guys are all still with me, right? Nobody's like saying anything or just talking to the air. No. So if you have one piece that's positive infinity and one piece that's minus infinity, then they don't cancel each other out. So as soon as you get one piece that's either positive infinity or minus infinity, whole thing diverges. So it's not like the minus infinity and positive infinity would cancel each other out. No problem.
Let's say, I'm sorry, if we got a 3 or 7 on the first part, we would have to continue going and find the other part.
Mm-hmm.
If the other part was infinity, we could diverge it.
Right. So if the other part was infinity, then it would diverge. Yeah. And what Brian is saying is that, like, so you can't say that positive infinity cancels out with minus infinity, because remember, infinity is a concept, and this is kind of what we talked about last class, right? If I have infinity minus infinity, I don't really know which one is bigger. So they're both very large, but like the first one could be bigger than the second one. They could be the same size, or the third one or the second one could be bigger than the first one. So you don't know what they are. So that's why, like, we can't ever say that infinity minus infinity, that the two things cancel each other out. Well, so we sort of already learned about infinity minus infinity in general, right? Like if you were doing a limit and it came out to be infinity minus infinity, that is one of the things where you'd have to like put stuff together and use L'Hopital's rule. This, you can't do that. So in this, it diverges isn't like a cop out. It's not like saying, oh, diverges doesn't mean like I can't figure it, like I don't know how to figure it out yet. Diverges is like the answer. It's saying basically like this does not, like this integral basically just blows up. There is nothing else I can do about it. So diverges is an answer. Yeah, I don't know if I have, I don't have a problem in front of me where I have two pieces where one of the pieces doesn't diverge. I will look one up and do it on Tuesday, first thing at the beginning of class. I'll do one where the two pieces, where like both pieces converge to a number. I don't have one off the top. I don't have one right here, and they're not super easy to just make off the top of your head. So, I have to think about it to find one that would do that. So I will find one. But more often than not, these diverge than converge. So, but I promise I'll bring one next class. All right. So I do have one problem left for us to do today. So 1 over e to the x. Well, so the problem with 1 over e to the x is you would like one. So it would be okay. I think 1 over e to the x. It would be okay on one of the ends, but not if you went from minus infinity to infinity. Because one of the ends, it's going to flip. I think it's going to flip back up. Because you would have 1 over e to the minus infinity, which then would just pop up to be an e to the infinity. So you kind of have to like tamper it down with something. Yeah, I just don't have one off the top of my head. But I will look one up. Okay. So I think this is D. The integral from minus 2 to 6 of dx over x minus 1 squared. Okay, so here, my bounds are fine, right? I don't have a positive infinity. I don't have a minus infinity. However, right, is that integral that I put up there, that function, 1 over x minus 1 squared, is that ever equal to 0? Yeah, I asked the wrong thing. Is it ever undefined? That's what I meant to ask. Not is it ever, you're right, it is never equal to 0. Is it ever undefined? That's what I meant to ask. Yeah, so it is. It's undefined, right? There's a place where this function, exactly, as not at 0, but at 1. So there's a place where this function, the denominator would end up being 0 when x is 1, right? So when x equals 1, this function is undefined. Okay, so 1 is the place we need to break stuff apart at, all right? So 1 is my bad spot. So I need to look at the integral from minus 2 to 1 of dx over x minus 1 squared, plus the integral from 1 to 6 of dx over x plus 1 squared. Now, I'm putting these two pieces together, and my function is undefined at 1. So the way that I wrote it right this second, you still have a bad integral because it's still undefined at 1, right? So sometimes you'll see it. It's not the biggest deal if you do this or you don't do this, but sometimes you'll see people say, I'm really going from 1 from the left side on this first integral, and then I'm jumping to 1 on the right side on the second integral. If you don't put the little plus or minus, it's not the end of the world. So if you're like, I know it breaks apart at 1, you're going to be okay. But sometimes the plus or the minus kind of helps you out some. So I'm going to put it there, but that's kind of why we're putting it there. We're putting it there because we know 1 is really a bad spot. So we're really thinking about breaking it into the left side and the right side. Okay, so this is now going to become the limit as b approaches 1 from the left of the integral of minus 2 to b dx over x minus 1 squared, plus the limit as, I don't want a b, as a approaches 1 from the right of the integral from a to 6 of dx over x plus 1 squared. You could use b for both of them, but then you got to really be careful about like what b is where, so I try to use 2 different letters. Let's come over here on the side and let's just integrate, figure out what this integral is. So I have the integral of dx over x minus 1 squared. So what do I want to do to integrate that? Yeah, so we're going to do a u sub. So u is going to be x minus 1. du is going to be dx. So this is going to be the integral of dx over u squared, or the integral of u to the minus 2. Oops, not dx. This should be du over u squared. So u to the minus 2 du, or u to the minus 1 over minus 1. So this is going to be minus 1 over u, which in our case is going to be minus 1 over x minus 1. So since I potentially need to integrate this 2 times, that's why I kind of come off around the side and do it that first time. So here, if we look at, so let's work on that first limit. Right, so we're looking at the limit as b approaches 1 from the left, and now we have minus 1 over x minus 1 evaluated from minus 2 to b. So this is going to be the limit as b approaches 1 from the left of minus 1 over b minus 1 minus 1 over minus 2 minus 1. So we're going to have the limit as b approaches 1 from the left, minus 1 over b minus 1, minus, so this is going to be minus 1 over minus 3, so the minuses are going to cancel, so just minus 1/3. And if I plug in here, I end up with minus 1 over 1 minus 1, minus 1/3. So I end up with minus 1 over 0, minus 1/3. And minus 1 over 0, that's infinity. So, and we're coming from the minus side, so we're getting here. And I have a minus on the top, so we get infinity minus 1/3, which is just infinity, and so right away I know it diverges. So I don't even have to do that other side again, because I know that that first side diverged. Questions? So you see this trick a lot of like 1 over 0 is infinity. It shows up a ton for us. And really we care about whether if it diverges or not. Okay, so the summation stuff, if you have like seen some Calc 2 before, and you're talking about converges or diverges with summations, that's what's coming after the test. Well, I should say, we're going to do a little bit of applications of integration, and then after the applications of integration, then we're going to jump into what is called series and sequences. And so series and sequences is when you have those summations and you're talking about converges or diverges. So that's coming. We're just not quite there yet. Other questions? No. Okay, so as I said, on Tuesday, I will bring a problem where you do the two sides and it converges to a number, so that you can see one where that happens. I want to take a couple minutes, right? I said at the beginning of class, if you were here, that I was going to talk about those homework problem videos that you guys are probably like, Dr. Orman, when are these coming? Because you keep saying they're going to come. So I sat down to do them the other night, and in section 8.2, you guys want me to explain every problem except number 1. And in section 8.3, you want me to explain 6 out of the 10 problems, which is not a problem, right? So I don't have a problem doing that. It's just that this is the first semester I did the thing with the videos, and so I assumed it would kind of be like, oh, if there's like 1 or 2 problems you guys still have questions to, because since I've worked out all the solutions for you to see, and so I figured, oh, they'll be pretty quick to make. So making a video with 1 problem or 2 problems is a lot faster than making a video with 10 problems or 6 problems. So they are coming. I promise they are coming. I will have the videos, so I owe you videos for section 8.2 and 8.3, and I promise they're coming. I hopefully should have them done over the weekend, and then I will post the link to them and send out an email. So I don't want you guys to think I forgot about you. I just wasn't expecting quite as many problems to go over. I'm not trying to say that's a bad thing, but also, right, like, so I think part of the problem in 8.2 is that a lot of people used a reduction formula where I, in the problem, didn't use a reduction formula. So I personally think reduction formulas are ugly, and so I only use them when I absolutely have to. And so if there's a way to do them without a reduction formula, that's why I did them without a reduction formula. It is possible that you did a reduction formula And that's okay, right? I've had a couple of people, like either email me or come to my office hours and be like, hey, I used a reduction formula on this problem. Is that okay? And so, yes. But I think that caused some of the confusion in section 8.2, because then 8.3 was a little better. But anyway, so I just wanted to kind of let you guys know that they are coming. I'm not just saying, oh, I'm going to make these and never make them. It's just that they took a little, what I thought